Welcome back, and I will now do that same problem in a much easier way. So the problem, let me clear it a little bit. So the original problem, we said, we apply some force to m sub 0, and that gives some acceleration, a sub 0. And then we said when we apply the same force to a combination of m sub 0 and m sub 1, we get 1/5 the acceleration. 1/5 a sub 0. And we worked it through with all the variables. What I'll show you is you can actually do this type of problem just by substituting numbers. And this is kind of quick and dirty, but it's good to do a reality check. And oftentimes you can solve the problem without having to go through all the variable mess. So I could just pick some numbers here. So I could say, well, what if F sub 0 is equal to 10 newtons, M sub 0 is equal to, 2 kilograms, and then A sub 0 is equal to, well, it would be 10 divided by 2, right? Because force is equal to mass times acceleration. So it would be 5 meters per second squared, right? And then in this case, we still have this would be 10 newtons. This would be 10 newtons. 1/5 a sub 0, well, there'll be 1/5 this, so it would be 1 meters per second squared. And then we could solve for what the new mass is. Well, how would we do that? Well, we have force, which is 10 newtons, is equal to the sum of the masses, so m1 plus m sub 0, but m sub 0 we already learned is 2 kilograms, times the acceleration, times 1/5 a sub 0, which is 1 meter per second squared. So then we have this 1, we could ignore it essentially. So then we essentially have that 10, and since all of our units are right, we can kind of drop the units because we know they work out. 10 is equal to m1 plus 2. So you get m1 is equal to 8. And then once again, if we want to know the ratio of m sub 0 to m sub 1, we can just substitute the numbers. M sub 0 is 2 kilograms. M sub 1 is 8 kilograms. So the ratio is 1 to 4. You probably find that a little bit easier. Let's do another problem. Another problem. Whoops. Invert colors. Okay. Let me get them. Okay. This next problem I think you'll find interesting. So let's say I have a skydiver, and he's in his skydiver position, falling towards the ground. And let's say he weighs 70 kilograms. So his mass is equal to 70 kilograms. Let's say that the terminal velocity is 120 miles per hour. So he's moving downward at 120 miles per hour, which is actually accurate. I've gone skydiving. 120 miles per hour. And if we convert that, you could convert that for fun into the metric system, but I'll do that for you. But it's good to know, just so you have a sense of how fast you fall when you skydive before the parachute opens. This translates to about 53.6 meters per second. I'm reading this from a problem from a website at the University of Oregon. But anyway, they are asking us, what force does air resistance exert on the skydiver? So let's be clear a couple of things. This 120 miles per hour, this is the skydiver's terminal velocity. And if you're not familiar with what terminal velocity is, I will now explain it to you. So when you fall from a plane, you have a bunch of wind pushing on you, right? You have a lot of wind resistance. The wind is, it causes friction. It slows you down, as you can imagine. I mean, that's how a parachute works. It just creates it allows the wind. It creates a lot more resistance from the wind, and then you slow down. So the terminal velocity is the velocity at which you no longer go faster than. So it's the velocity at which you stop accelerating, or it's the velocity you reach and you don't go any faster than that. And it's basically based on your wind resistance. So at the terminal velocity, your acceleration is 0. Acceleration is 0. So what we know is that the force of the air, we could call that the air force. So we know that the force of the air is exactly equal to the force of gravity. The force of gravity. And how do we know that? Because the guy is not accelerating. It's his terminal velocity. He's at a very high speed. He had accelerated all the way to this point, but the more he accelerated and the faster he got, the more resistance the wind provided up to a point where the wind provided so much resistance that he stopped going any faster. And that's the terminal velocity. So at terminal velocity, the force of the air is equal to the force of gravity. And what's the force of gravity? Well, the force of gravity is just the guy's weight. So the force of gravity is equal to the guy's mass, 70 kilograms, and we have our units right, 70 kilograms, times acceleration of gravity. Well, the acceleration of gravity is 9.8 roughly meters per second squared. We could use a calculator to calculate this. 70, I feel cheap now, I could have done it by hand anyway. 686. So it equals 686 newtons. Now the second part of the question, and this is interesting. If the skydiver pulls in their arm and aims their body downward, so now the skydiver looks more like this. And he pulled in his arms and he aimed his body downward, right? So he's diving really. The terminal velocity can be increased to about 180 miles per hour or 80.5 meters per second. They give us this. We could have figured it out though. So now he's going a lot faster, almost, but roughly 50% faster than he was, or maybe, well, 30% faster than he was going before. He's going a lot faster. And why is that? Because he's more aerodynamic now. He's, and we'll do more on pressure later, but I want you to get the intuition that, when you're laying flat, there's just a lot of wind pressing against your body. You have a lot of surface area exposed to the wind. But when you're diving in this situation, like the skydiver is, he has a lot less exposed to the wind, really just his head. His head is breaking the wind and nothing else. And that's why it takes a lot more speed for the force of the wind resistance to match the force of gravity. So the question is asking, if the skydiver pulls in their arms and aims their body downward, the terminal velocity can be increased to about 80.5 meters per second, or about 180 miles per hour. So it's going very fast. What force does air resistance now exert on the skydiver? And I'll let you think about that for a second. Maybe you want to pause it and think of it yourself. And now that you've unpaused it, I'll tell you that this is a trick question. Because once again, the skydiver has reached a new terminal velocity. By definition, at the terminal velocity, the skydiver is no longer accelerating. The skydiver is not going any faster because the wind resistance is so strong that it completely matches the force of gravity. So once again, the wind resistance, the force of the air or the force of the wind, is equal to the force of gravity. And what is the force of gravity? Well, that's his weight. And we already figured that out. That was 686 newtons. And I know what you're thinking. You're saying, Sal, this doesn't make sense. He's now going so much faster. Doesn't the air exert more force on him? Well, no. The air is exerting the same force. If he was going that same speed, but he was flattened out, I would agree with you. The air would be exerting more force on him. But what's happened now is that he's once again reached a state where his acceleration is zero. It's at a higher velocity, and I want you to think a lot about this. He's at a much higher velocity now. On his head, for example, there's a lot more wind going by, but it's pressing on a smaller surface area, right? And I'm not going to go too much into detail of pressure right now, but I want you to get that intuition. So, although the wind is going a lot faster, it's going a lot faster on a smaller area, and its actual force is the exact same thing. And we know that because he's not accelerating anymore, because he's at his terminal velocity. So think about that a bit. It's a bit of a trick question, but I think it gives you a good intuition on what acceleration means, what terminal velocity means, and it'll start to give you a little bit of an intuition on even wind resistance on pressure. I'll see you in the next video.